Okay, so this is our first lecture for chapter 10. And so chapter 10 is all about graph theory. And so when mathematicians or computer scientists talk about graph theory, they don't mean graphs in the traditional sense as in the graph of a function. And so this is probably better referred to as combinatorial graph theory. And so in combinatorial graph theory, what is a graph? Well, it's best to just begin by looking at a picture. And so a graph is going to be a collection of points, which are called vertices. So let me call this point A, point B, and point C. Along with a collection of edges which connect these points. Right, and so you don't necessarily need an edge between each point. For example, maybe there's a line connecting A to B, and a line connecting point B to C, and these are called edges. Right. So maybe this first edge is E1, this second edge is E2, and I have a set of two edges right, for this picture. Right, and so for example, these things can be used to model maybe computer networks, like maybe each vertex is a different computer and each edge is a network that connects, or is some connection between the different computers. Right, and so notice that, right, so for example, let's say I focus on the edge E1, right, so I have this connecting point A and to point B. So the main distinguishing feature of E1 is just the 2 points that it connects, right? And so I can think of E1 as just the set consisting of A and B, right? And I can identify edges with a choice of some collection of pairs of vertices, right? So some subset of size 2 of the vertices, right? Okay, and so this is sort of basic summary of what a graph is, and so now we're going to go into more detailed definitions. And so these are the main mathematical objects we'll be talking about for all of chapter 10, basically. And so what is the more formal definition of a graph? Well, a graph we will typically model as a set of vertices and edges, right? Usually we'll use G to represent a graph. And it's going to consist of a pair of sets where V are the vertices and E are the edges, right? And so we're going to assume that each edge, meaning each element of the set E, has one or two vertices associated to it. Right, and so in the example above, well, we have two edges, and each of them has two vertices associated to it. So in this particular case, we would refer to the graph as a simple graph, right? So if all edges have two vertices associated to them, or connect two vertices, the graph is called simple, right? And so you may think, well, above I said that, right, for each edge you can view it as a collection of two vertices. How does it make sense to talk about an edge associated to only one vertice or one vertex? Well, for example, let me return to the picture above, and let's add an edge that just connects A to itself, right? And so now if I add this, oh, sorry, I shouldn't have drawn that arrow. Right, so now if I add this edge, right, so this edge, which I'll call E3, connects A to itself, right? And so we can just view this as the set A by itself. However, if we have such an edge, this is no longer a simple graph, right? In order for it to be simple, there can't be an edge just connecting one vertex to itself. In terms of graph theory terminology, what do we usually call these things? Well, these things are usually called a loop, right? Just because it looks like a loop, right? So a loop is some edge that connects a vertex to itself, right? And so just a quick summary, well, a graph will have a collection of vertices and then a collection of edges, which may not connect all the vertices, just some subset of the vertices. And the edges are allowed to connect either two vertices or just connect one to itself. If there are no loops, then it's a simple graph. And if there are loops, it's just a graph or not a simple graph. Right. So what we are not allowing, though, is, for example, to have, at least in this definition, to have, say, like 3 different edges between A and B, or an edge that connects 4 or 5 vertices or something like that. So those are more complicated objects, which may be interesting, but we're not talking about those yet. Okay, and so another important type of graph, which we've actually already encountered is something called a directed graph. And so it turns out that directed graphs are basically the same as relations, which we spent some time analyzing in chapter 9. And so what is a directed graph? Well, it's going to have the same basic structure as what we just looked at. So it's some graph, meaning a collection of vertices and edges, but we're going to assume that the edges have a direction associated to them. Right, and so what does this look like? So maybe my vertices are, again, say A, B, and C. Well, maybe I have an edge connecting A and B. In a directed graph, there's going to be an arrow telling you which way the edge goes, right? And so in particular, well, notice I drew an edge connecting A and B that starts at A and ends at B. Well, I can also start at B and end at A. And since the arrow in this case is pointing in a different direction, this is a different edge, right? So if you have a different direction, it counts as a different edge in a directed graph. And in particular, we are allowed to have 2 different edges connecting the same pair of vertices as long as they're going in 2 different directions, which is different than what we saw in the previous definition. Right, and so maybe I also have, say, an arrow going from A to C, and then maybe C is related to itself, or there's an arrow from C, an edge from C to itself. Right, so this is an example of a directed graph. Right, and so right, so how do these connect to relations very quickly? So this is a pretty important observation. So a directed graph is really the same as a relation on the set of vertices. Right. Right, and so how do I define this relation? Well, I say that one vertex is related to another if there's an arrow starting at the first vertex and ending at the other, right? So for example, in the picture that I just drew, what is the relation? Well, I have an arrow from A to B, so I get the pair AB. I have an arrow from B to A, so I get BA. I have an arrow from A to C, so I get AC. And finally, I have a loop at C, which just connects C to itself, right? So that would be the relation on the set V that's induced by this graph, right? And so you can go back and forth between directed graphs and relations, and we already even saw an example of this in chapter 9. Right, and so one more comment related to something I mentioned on the previous slide. So remember, for undirected graphs, well, what is an undirected graph? It's just the graphs that we saw on the previous slide where the edges have no direction. Right, so the edge is you can think of an edge E as a pair of 2 vertices, or maybe just a singleton set of 1 vertex if there's a loop. Right, so this would be the situation of a loop. Well, in the case of a directed graph, we can't just model the edges using a choice of 2 vertices or a subset because the order matters, and so therefore we use ordered pairs, right? So sort of like what we just saw below, right? So we'll use ordered pairs, right? And so in particular, these two things are different, right? So the first means that I have an arrow from A to B, and the second means I have an arrow from B to A. And so that's the main distinction. Yeah. Okay, and so let's now move on to some of the main important terminology for graph theory. We've already discussed some of the basic terminology, but there's a lot more to talk about. Right, and so the first important notion to discuss is the notion of neighbors in a graph. And so let's suppose I have a graph G. Right, and so suppose that U and V are vertices on G. Right. Well, U and V are said to be adjacent or neighbors if there's an edge connecting them, right? Right, so for example, let's suppose I have the following graph. Say I have some vertex U, some vertex V, maybe some vertex W, and a vertex X. And say I have an edge between U and V, edge between U and X, and then an edge between W and V. So this is an undirected graph, and it's also simple because there's no loops. So what are the neighboring vertices or the adjacent pairs? Well, U and V are adjacent because I have an edge between U and V. U and X are adjacent, and also W and V are adjacent. Right, because each of these pairs has an edge connecting them. Right. And so another common bit of terminology we'll often see is, well, suppose I have an edge E, right? And in this case, let me call the edge this. Suppose edge E is an edge that connects two vertices, say U and V. You'll often hear people say that E is incident with U and V. Right, so incident means like there, or some kind of incidence just means there's some like intersection or interaction or connection between the two, right? So this is another common bit of terminology. Right, and so if we have, let's say we fix a particular vertex, we'll usually use the notation n of v to denote the set of all neighbors or adjacent vertices. To V, right? Right, so if I pick a particular vertex V, the set n of V is the collection of all neighbors of V, meaning all adjacent vertices or all vertices that are connected to V by an edge, right? And so in this example, right, so let me calculate the sets. So for example, what is n of U? Well, n of U is going to be the set of all vertices to which U is connected, while U is connected to V and U is connected to X. So this is going to be the set V and X. What is say n of X? Again, all the vertices that X is connected to. So in this case, it's just connected to U. And so on, right? Sorry, just pause for a second. Right. One thing Right, so one thing that I want to point out that I haven't demonstrated in an example, let's say I have another vertex here, which I'll call Z, and let's suppose that Z is not connected to anything. That's allowed, right? You're allowed to have some vertex that's not connected by an edge to any other vertex. And so in this case, well, what would the collection of neighbors of Z be? Well, if Z is not connected to anything, then there are no neighbors, and therefore the neighbor set is empty. Right? So it's the empty set. Right? Okay, and so right, so it also makes sense to talk about not just the neighbors or the adjacent vertices of one particular vertex. It also makes sense to talk about the neighbors or adjacent vertices of an entire subset, right? So suppose I don't just have one vertex, but suppose I have a whole subset of the set of vertices, right? So V is going to be my vertices, right? And so what is we can define the neighbors of everything in this set, usually denoted N of A, to just be the union for every vertex in A of the neighbors associated to A. Right, so if you go back to the previous example on the last page, you can check, or if you rewind the video, you can check that if I look at the neighbors of the set U and V, well, what would I do? I calculate this by taking the neighbors of U and I union it with the neighbors of V. And so we saw that the first was Vx and the second was UW. And so the union of these two is Vx, U, and W, right? Okay. All right, and so another important quantity related to a graph is something called the degree of a vertex, right? And so what is the degree of a vertex? Well, we're first going to be talking about the undirected situation, and then we'll modify what we talk about to work for directed graphs, right? So let's suppose I have a graph G, and let's fix some vertex V, right? So some particular element of the set of all vertices, and so the degree of V is the number of edges that are incident with V. Right, so it's the number of edges that connect to V or that leave from V. And so there's one important special case. If I have a loop at V, meaning, right, so I have V and I have a loop from V to itself, loops count twice for the degree. Right, and the reason for this is if I zoom in, we want to think of the degree as like the number of edges leaving the vertex. So if I zoom in on this picture over here and if I look at the vertex V, well, if I have a loop, if I magnify, there's one bit of the loop leaving from this point and another bit leaving this point. So it makes sense to count this twice if we're just interested in like the number of lines that are leaving V, which are the edges. Okay. And so let's look at an example of calculating degrees. So suppose G is the following. I don't need to write that. Right, so suppose G is the following graph. So I have U, V, W, and say W has a loop. U is connected to V, W is connected to V. Sorry. And let's say I add in a final point X over here. And so this is my graph. And also let's say I have another point as before, some point Z, which is sitting off, not connected to anything, which is allowed. Right, so let's calculate all these degrees. So what is the degree of V? right? Well, I want to look at V and I want to see how many edges are connected to V or how many edges or lines are leaving V. Well, in this case, I see there's 2, so the degree is 2. What is the degree of W, right? Well, W is connected to U and W is connected to V, so that already contributes 2. And I also have a loop at V. And so remember that loops count twice, right? So this should be 4, right? Because loop counts as 2, right? And so also, what is the degree of X, right? Well, X only has one edge connected to it or one edge leaving it, so the degree of X is equal to 1. But what about if I wanted to calculate the degree of Z, right? So Z is this point that's sitting away. Sometimes this is referred to as an isolated point, meaning there's no edges connected to it, so it's not connected to the rest of the graph. Well, in this case, since there's no edges connected to it, we would say the degree is 0, right? Right. Right, and so again, remember the best way to understand this is imagine like you want to calculate the degree of a particular vertex. Imagine zooming in on the point, for example, zoom in on the point W here, and you count the number of lines that are leaving the point, right? So this will make it clear why you want to count a loop twice, because for a loop, there's going to be associated to that loop, you have 2 lines leaving W. Right. Okay, and so this brings us to the first theorem that we can actually prove about graphs. And so this is something that's typically called the handshaking theorem. And so the theorem is the following. So let's suppose I have an undirected graph, meaning, right, the edges don't have directions. And suppose that it has m edges, right? So the set of all edges has cardinality m. The theorem is that if I multiply the number of edges by 2, or if I look at 2m, that's the same as the sum of all the degrees. Right, so remember, so my graph has vertices set V and edges are the set E. And so I'm told that the cardinality of E is equal to m. And so what the theorem says is that if I sum up all the different degrees, so this sum ranges over each vertex or each element of the vertex set. If I sum up all the degrees of all the vertices, that has to equal 2m, or twice the number of edges. And so what's the proof of this? So it's relatively straightforward. And so the idea is that, well, if I have, well, if I have an edge, how many vertices, or how much does the edge contribute to the count of the degrees? Well, what can the edge look like? So there are 2 possibilities. So either there's some, say, V1 and V2 that E is connected to, or maybe E just happened to be a loop, which is allowed, right? Right, so maybe E is a loop from a vertex to itself. Well, in both cases, it contributes 2 towards the total count of the degrees. Right, in the first case, well, I'm going to count, right, I count 1, E contributes a count of 1 towards V1, and E contributes a count of 1 towards the degree count of V2. In the second case, E contributes a count of 2 towards the degree count of V2. Right, and therefore, since for each edge, each edge contributes a count 2 to the sum that I'm now circling in red, right? Each E contributes a count 2. Well, then when I sum up, or if I sum up all the degrees, that's going to be the same as just multiplying the number of edges by 2, right? Because m is the number of edges. For each such edge, I count 2 I have a count of 2 contributing to the total count of the degrees. And so therefore, when I sum up all the degrees, that's going to be the same as just multiplying the number of edges by 2, right? Because for each E, I get a count of 2 to the total degree count. Okay. And so one consequence of this theorem, so this is the following corollary, right? And so in math, a corollary is usually some useful piece of information that follows easily from a theorem, right? So this is a corollary of the previous theorem. And so the corollary is the following. So suppose G is an undirected graph. Right. So the theorem is that, or the corollary is that G has to have an even number of vertices of odd degree. Right. So if I have just an arbitrary undirected graph and I collect all the vertices which have odd degree, then the corollary or the theorem is that there have to be an even number, right? So I can't have an odd number of vertices which have odd degree in a graph, no matter how you draw it. And so the proof of this, well, we just use the previous theorem, right? So from before, right, let's suppose the cardinality of the set of edges is equal to M. Well, from the previous theorem, if I multiply that by 2, then this is equal to the sum of the degrees of all the vertices, right? And so what I'll do is, well, I'm interested in understanding vertices with the number of vertices with odd degree. So what I'll do is I'll break up this sum into 2 parts corresponding to whether or not the degree is even or odd. Right, so the first sum I'll have V with an even degree, right? So, right. And then I'll add on the remaining terms, which are the terms with an odd degree. Right, and so since the degree is an integer, it's either going to be even or odd. So you can always, and it's not going to be both. So you can always break up the sum in this way. Right, and so, well, let me look at the first sum over here. Well, I'm adding up, right? So these by choice, these are all even, right? So by definition of the sum, each of the terms I'm adding here, each of the degrees is an even number. And so if I add a bunch of even numbers together, it's always even, right? So this sum is even. Well, on the left-hand side of the equality here, well, no matter what M is, 2M is always even, right? And so since I can write, since the remaining terms, since the first 2 terms here are even, the remaining term has to be even, right? Right, because I can write the sum over the odd degrees as 2M minus the sum over the even degrees. And if I subtract 2 even numbers, I get another even number, right? So the third term here has to be even. But, so this is the key point, even though this sum is even, each of these terms is odd. And so therefore, there have to be an even number of vertices of odd degree. Otherwise, you would get a contradiction, right? Right, so let me just write this out. So let's say let's VO equal set of vertices of odd degree. Right, and so if the cardinality of V0 were odd, the third term would be odd because I'm adding an odd number of odd numbers, right? But that's not possible because we just saw that it has to be even, right? And so that's the proof, basically. Okay, and so we've been talking about degrees of undirected graphs. So now I want to talk about degrees of directed graphs. And so in this case, we'll fix a particular directed graph, right? And so remember, you have to be a little bit careful because for a directed graph, the edges have a certain direction associated to them, and you want to take that into account when you're talking about degrees of vertices. Right. And so it will help to introduce just a little bit more terminology. So let's say this is an edge in my directed graph, say an edge from U to V. So U is typically called the initial vertex for E. And V is usually called the terminal vertex for E. Right? Initial because that's where the E starts, and terminal because that's where E ends. Right? And so given a particular vertex in a directed graph, there's actually going to be two different types of degrees we're going to assign, depending on whether or not that vertex is an initial or terminal vertex. And so the first notion, right, so let's fix some V in the vertex set. The first notion is something called the in degree of V, little v. Right? And so this is usually denoted by degree with a plus sign of V. And so this is going to be not the total number of edges connected to V, but the number of edges that have V as their initial vertex, or that leave V. Right? On the other hand, the out degree of V is exactly what you can imagine. It's going to be the opposite. So this is usually denoted by degree minus of V. And so this is going to be the number of edges that have, oh, sorry, I got this backwards. So the first bit should be terminal, excuse me. It's very easy to get these flipped around. Right, so sorry, the in degree of a vertex V is going to be the number of edges that have V as their terminal vertex, or the number of edges that end at V, right? So, I mean, one way to remember is sort of they're going into V, so the arrow is pointing into V. The out degree is going to be the number of edges that are leaving V or going out of V, right? And so this is the number of edges that have V as their initial vertex. Sorry about the mix-up. Right. Right, and so the slightly complicated thing with directed graphs is when you're talking about degrees, you have to remember that for each vertex there are two notions of degree that you have to deal with. The in degree, meaning the number of edges that are going into V, and then the out degree, which is the number of edges that are going out of V or leaving V. Right, and so let's do an example. Right, so let's say, let me try to fit this example into this page. So let's say this is my graph. I have some U, V. Let's say I have an edge connecting U to V and also V to U. And then maybe there's a third point, W, which is connected to V. And then maybe W is connected to itself by a loop. Right, and so I haven't said how to calculate degrees of loops for undirected for directed graphs. I'll explain how to do that in a second. But let's first look at the degree of U and V, right? Well, there's two notions of degrees. So what is for example, the in degree of U? Well, I want to look at the total number of edges that begin that end at U, right? So that have U as their terminal vertex. And so in this case, there's just one. It's the edge from V to U. So in this case, the in degree would be 1. What about the out degree of U? Well, how many edges are leaving U? In this case, there's also just 1, right? So it's 1 in both cases. Let's move on to V. right? So let's look at the in degree of V. Well, for V, I have an edge from U to V and also an edge from W to V. So there are two edges that are going into V. So this should be 2. And what is the out degree of V, right? Remember, this is the number of edges that are leaving V. Right, well, how many edges are, excuse me, how many edges are leaving V? There's exactly 1, right? Because I just have an edge from V to U, right? And so, right, so what happens if I wanted to calculate, say, the in and out degree of W? Right, so the issue here is that there's a loop at W, right? So I know, for example, that the out degree is going to be at least 1 because I have a vertex leaving W and going to V. But how do I count the loop? Well, remember, you want to think about what happened when we counted loops for undirected graphs. We wanted to take into account, we wanted to sort of view the loop as two different lines that are leaving W. And so sort of look at the picture locally, zoom in on the vertex and think about how many edges are leaving or going into W. And so in this case, if we do that, well, the main thing we have to take into account is that there's an arrow associated to this W. And so let's follow this arrow along, right? And so if you look near the point, there's going to be one point where the loop is leaving in its direction, going out of W. And then there's going to be, when you follow along the loop, there's going to be near the end a point where it's going back into W. So you can view a loop as both, for this loop, you can view W as both an initial and terminal vertex, right? Because it's an initial vertex because the loop leaves W in a particular direction, and it's a terminal vertex because the loop ends at W, closes back in on W. And so therefore, we're going to count loops, 1 count for each, right? So if I go back to the definition of in degree and out degree, so a loop counts as 1 for each. Right, so if I have a loop at a particular vertex, that loop will add 1 to the total in degree, and it will add 1 to the total out degree. And so then, well, what is the total in degree of V, or sorry, in degree of W? The in degree is the number of edges that have W as its terminal vertex. Well, if you look at this picture, there's only 1, which is the loop, right? So the loop contributes 1. And then what is the out degree? Well, I have an edge from W to V, and then I also have the loop, which is leaving W, so the out degree is 2 for this example. Okay, and so if you think back to the handshaking theorem from the previous pages, there's an analog of this for directed graphs. And so the theorem is the following. So if I take the cardinality, right? So here I have some graph G, which is V and E, set V of edges, or V of vertices and E of edges. And if I take the cardinality of the set of edges, then this is always equal to the sum over all the, I can never remember this, right? The sum over all the in degrees of the graph, and it's also equal to the sum over all the out degrees. So these two sums are the same, and they're both equal to the number of edges, right? So if I sum up over all the vertices in the graph, I sum up the in degrees, then that's the same as summing up all the out degrees, and both of those sums are equal to just the number of edges. And so again, what is the proof? The proof of this is very similar. So suppose to what we saw for the case of undirected graphs. Well, suppose I have an edge. Well, it's either a loop or it's not. Let's first suppose it's not a loop, right? So then there's a pair of two vertices that E connects. And so, right, and so, well, over here, this is E is ending at V2, so this count adds count 1. Right, so this contributes 1 to the n degree, which is degree minus sum. On the other hand, over here, the initial point of E contributes 1 towards to the total overall degree plus sum. Right, so what I mean by that is when you look at the degree plus sum, there's this vertex, or sorry, this edge E is going to contribute 1 to this total sum, right? And so each edge will contribute 1 to the total sum of degree plus and 1 to the total sum of degree minus. And so therefore the number of edges is exactly the same as the whatever value you get by summing these all up, right? Because each edge will contribute 1 value to each of these two sums. And so what happens in the case of a loop, right? Well, if you're in the case of a loop, then there's just one fixed vertex, right? Well, it's still the case that, right, if I follow this edge along, it's still the case that E will contribute 1 to the degree plus or toward the out degree from over here, and then also 1 towards the in degree from over here. So it's the same, right? So the case of a loop is the same. Okay, and so just to end the lecture, I just want to briefly mention some important types of graphs which will show up commonly as examples. Right. Right, and so we'll encounter a variety of other different important types of graphs throughout the next several lectures. Today, I'm just going to introduce two. So the first is something called a complete graph. Right, and so let's suppose I have a vertex set which has size n, right? And so the complete graph on n vertices, oh, sorry. Is the graph that contains exactly one edge for every pair of vertices, right? So it basically has all the possible edges. Right, and so so this is typically right if the set of vertices has size n, this is usually denoted by k sub n for complete. You would think c sub n, but we're going to look at an example after this where it's c sub n is the common notation, right? And so so what is k1? Well, if k1, there's just one vertex, so it's just a point. What is k2? Well, in K2, I have two vertices and then a line connecting them, so it looks something like that. What is K3? Right, so I need to connect all the different edges, all different possible pairs of edges, so it's just going to be a triangle. Right, and so K4 gets a little bit more interesting looking. So I have, in this case, I have 4 vertices. I mean, the initial thought is, okay, well, this is going to be a square or something close to a square. But remember, I have to connect every single pair. So I also have to connect the corners. So it's actually going to look like this. And then let me just do one more. So let's do K5. So in this case, I'll have 5 vertices. Right. And so what is K5? Well, I have to connect every single pair I can find. Right. So you get some kind of pentagram type thing. right? So that's K5, and so on, right? And so one thing to point out is that, well, how many edges are there? Well, since I have one edge for every single choice of two vertices, right? But for any given two vertices in the complete graph, there's an edge connecting them. So that means that the number of edges in the graph is exactly the same as the number of pairs of vertices, right? Because for every pair of vertices, I have to have an edge, right? So the cardinality of E is always equal to n choose 2 for complete graph, right? Because I have n vertices, and for every choice of two vertices, I have an edge, and so that's where this comes from. Okay, and then finally, the next example, which we'll end the lecture with, right, is a type of graph called a cycle, right? And so Cn is the graph. I'll write this out abstractly, and then we'll look at pictures, and it'll become clear. So it's the graph G equals VE, where I'll label my vertices as V1, V2, and so on up to Vn. And then, well, what are the edges for this graph? So the edges are consecutive. I have an edge between consecutive vertices given this listing, right? So I have an edge V1, V2. I have an edge associated to V2, V3. I have an edge associated to V3, V4, and so on until I get to Vn minus 1, Vn. Right, so what is, for example, C3? Well, I have V1, V2, and V3 as my vertices, and then I have an edge V1 to V2, I have an edge V2 to V3, and I have an edge V1 to V3, right? And so in fact, C3 is the same as the complete graph with 3 elements that we saw before. But that's not always the case. For example, let me draw C6. So in this case, I'm going to have 6 different vertices, right? So V1, V2, V3, V4, V5, and V6. And so what are the edges? Well, I have to connect V1 to V2, then I connect V2 to V3, then V3 to V4, then V4 to V5, then V5 to V6. And then you also want you want to end the cycle, so I want to connect V6 back to V1, so I forgot to put that here, right? So I go up to Vn minus 1 to Vn, and then finally I connect Vn back to V1. Right, and so these are called cycles, right? Because you have basically like one large loop or cycle through the collection of vertices, and there's no more complicated relationships. All right, so that's it for today. And so the next lecture will basically all be focused on another very important type of graph, which is called a bipartite graph.